Hey, John here. This is the retro board that we're talking about, and this jumper right here is going to come up in our conversation. So let me make sure that we all remember what I'm talking about. Jumper 11, J11 is this guy right here. Remember, if you put a jumper between the middle pin here and the one on the left, you are connecting this A right there. Let me see if I can zoom in on this thing a little bit. Here we go. Let's say we open in a new tab, click on it like this. Oh, yeah, okay, zoom a little bit. Okay, there we go. What do we got here? Okay, so this is J11. It says J11 right there. This 2x3 header. The A right there refers to the port A in the SIO chip, which is this thing over here and marked right there. Okay. This selects how the baud rate clock is going to be generated for the SIO. Put a jumper on this side over here. It's connected to X2, which is this part right there, which is the baud rate oscillator. Okay. If you put the shunt between the middle and the one on the left, we're looking at the CTC output for port A, which is channel 1 of the CTC chip right here, okay? So when we talk about some of the stuff I'm going to be mentioning, J11, just remember that's the one here. Port A is the serial port that comes out of this connector right there when we're talking about serial I/O. Just a refresher, I talked about all this stuff in the recording on how the SIO port works earlier, right? Here's port B of the SIO over there. It has 2 serial ports, but we really only care about this one right now, okay? So let's have a look at a new GitHub repo that I created the other day, all right? Apparently 4 days ago. And I've been updating as recent as 1 hour ago while preparing for this recording, okay? So in this repo, I'm going to evolve a BIOS and a bootloader for CPM, okay? So this is where the whole CPM operating system stuff is going to go. Right now, I have a bootloader here. We would call that a first stage bootloader. This is what will go into the flash to load a operating system image off of the SD card. That's what's going to go in this directory here. This hello application right now, let's have a look, see where we're going before we get there. This file right here is our stand-in for an operating system, okay? So what is this operating system going to do? It's going to start up, it's going to print out hello from the SD card, and then go into a spin loop, okay? So let's talk about what we need to do to get to the point where this is going to run. This is going to come in 2 pieces. One is, how do we talk to SPI devices, which is how we're going to talk to the SD card. That's what I'm going to talk about today. And then we'll go over the SD card stuff, which is a bit more complicated. That's best left to recording a video on its own. All right. The library directory right here has code, most of which we've already seen. This is a minor changes, a little bit cleanup of the code that I wrote to validate the board itself. And the Z80, 2063 Z80 repo without the CPM after it over here. There's some testing code in there that I used to validate the board, right? So I refactored it a little bit, and this is where this stuff came from, okay? The CTC code that I talked about before is exactly the same. I broke it into 3 separate files so that if I want to use it, I only have to bring in the code for the one port I'm going to use. And right now we care about only port 1. And we talked about this before. All this is going to do is fire up CTC1 and set the divisor to whatever is in register C when this is called. This is used to generate the baud rate clock that comes out on the left side of J11 that we were just looking at for SIO port A. Okay, so all we need to do is remember the fact that that's what this thing is for. Just a quick reminder, okay? And right now I don't care about these other ports, but this is cut and paste right out of the code we saw before. Hexstop.asm is cut and paste out of what we saw before. If you went through it and figured it all out, great. I kind of glossed over it. I'm not going to get too much into the details now, other than to point out that I saved the accumulator and flags and restore them here in this routine because as we watch along for the debugging code, I tend to call this a lot, and it got real noisy, so I decided to just save the accumulator every time this is called. Okay, on these machines like the Z80, there's not a lot of memory, so you don't really want to use the stack. You don't want to put a lot of stuff in the stack unless you really need to. So it's this never-ending battle. Do I save all the registers in a subroutine that might modify them, because this is obviously going to modify the accumulator, and then restore them, so that when the caller, you return back to the caller, how the registers could be messed up or not. I don't know. And sometimes you don't, because, again, it's a precious resource, memory. You don't want to waste it. And it also takes time to save and reload. Argument here is, I call this from so many places, and in almost every time when I'm debugging, I really want to save everything and restore it. And pushing and calling and popping over and over and over and over again actually wastes more memory for all the push and pop instructions than it does to just do it once in here. And in terms of speed, we're printing to a serial port that's running at an insanely slow rate. Slowing this down is really not a big deal, okay? So I went ahead and saved it in here. I guess one last little tidbit. This doesn't call the SIO stuff anymore. I decided to come up with a generic label for the routine that is used to print one character. All right? And I call it that. We'll see that in a second when we look at the updated SIO code. And the other thing about the SIO code is I just remembered while looking at this, I now print the value in the C register when I'm in that code. And I think before it used to print from the B register. I made that change because the CPM BIOS wants to print stuff from the C register. It turns out that the code in the SIO thing doesn't really care what it comes in, and so it dovetails in better down the road if I make this change now. Okay? So that's what's going on in the hex dump routine. It still works the same way. I call this, I put our address in the HL register pair of the memory byte, the first byte of a plurality that I might want to print out in a dump, and then I put the number of bytes that I want to print in the BC register pair, and I set the E register to 0 if I don't want fancy print formatting, or I set it to 1 or some non-zero value if I do want to print out fancy format. And the difference between fancy and not fancy has to do with this code in here, which decides to print it wants to print rectangular hex dumps, and it puts an extra gap between bytes 8 and 9 so that it's easier to read the output. The value of having both options is that in a debug routine, we might only want to print out 8 or 9 bytes, and we don't want to have to print out a whole chunk of stuff, and we don't want the fancy print formatting getting in our way. Okay, so I wanted a way to shut that off. I think that was in the old code as well, so not a big deal. No changes to io.asm. This is interesting. Thank you, GitHub. Reload the page. Okay, we're back. And this is the same stuff we saw before. I enumerate all the ports. I give them all names and equate them to their I/O ports based on the schematic drawings. And I have these constants in here that represent the bits positions of every one of the I/O port bits. Again, we saw this once before, I believe. No changes there. Memory.asm is new. This is actually going to be used when we actually worry about the CPM BIOS. And yes, and also the bootloader where we're heading, okay? The bootloader is going to read some memory, some stuff off the SD card into memory, and then it's going to jump and execute it. So this address right here, the load base, is the address where the data is going to be loaded from the SD card, which when we get there, spoiler alert, is going to be the entire copy of the whole CPM BIOS. And the way those things work in the old days, it was very simple. You just read the whole thing in verbatim binary. There's really no fancy startup. You just copy it in off the disk and just branch to the entry point address, and it's off to the races, okay? So anyway, memory.asm defines those constants that we will use to know, so we know all the different modules, right? The boot code knows where the CPM OS is supposed to be located. And then when I compile the CPM code, I need to make sure that it agrees with where the bootloader thinks it's supposed to go. So all the addresses and stuff line up. And the goal is to have one and only one place where you actually specify certain addresses, like where the thing will load and where the CPM, CCP begins and stuff like that. All right. This will make more sense when we get to the point where we're actually booting up CPM. But that's what this file's for. Here, that's a new one. That's a new one. And what do we got? SIO is the same one, except of printing the character in the C register. These routines are a little different than they used to be, but they're really doing the same thing. This one, I want to print the character that's in the C register as opposed to the character in the B register. And you'll see I made some adjustments in here to make that happen. Okay. What do? They wait for the thing to be ready. And then if it's not ready, they go into a spin loop here waiting. When it is ready, I put the character to print in the accumulator, and then I just print it, send it out to the SIO. Okay, here's the contx char that I mentioned earlier. I wanted to have a label that just simply said, print this to the console, right? I didn't want to have to weld into all the code everywhere the fact that it's on SIO port A. So I just simply put both of these labels in the same space. That way, con transmit can be used kind of universally. This is pretty handy because some of the test routines, when I tinker around, I don't necessarily want to use this SIO driver, okay? As long as you have some code somewhere with this label in it, like this, that says, hey, this is where the contx char routine is, then it'll use that one, okay? That's why I put this in here. So this is one of a possible multiple different ways that you could code up something so that it gets printed to the console. And that is why hexdump ASM simply calls that and doesn't care how it's going to get to where it's got to go. All right. Okay, so those are all the things we've seen before. What is new? This is some stuff we might have seen before, but this is a new one here. Let's look and see what this one does. This I might have stolen from Leventhal. If we go back to the Z80, how to write Z80 assembler, I just did a Google search on this. This guy here, Leventhal, if you don't like, reference manual style education, which is actually what I grew up with, what I know, and what I'm happy with. I may not be thrilled with it, but I can get by with that, right? And the data sheets are free and all this other stuff. If you want a book, that's the guy right there. In those days, that's the guy. This is the book right here, Z80, Assembly Language Programming by Lance A. Leventhal. And he has two different editions here. I don't know what the difference is. Maybe there's second edition, or maybe changed publishers. I don't know. Anyway, I had a copy of it. I can't find it. I was hoping to open it up and brag. Yeah, I still have mine. I don't know where it went. Maybe I lent it to somebody. It didn't come back. I remember this one too. Z80 Assembly Language Subroutines. I think that what I'm about to show you is an artifact of my memory of one or the other of these books, is my point. If it didn't come from this guy, by the way, this is the book for CPM. I actually have a lot of these books. I actually have this one. I got that one. If you scroll around in here, there's probably a whole bunch of CPM books lying around the shelves down here in the old basement. But this is the only one you need. Let me rephrase. If you're going to write your own BIOS, this is the book. Okay? You can use the digital research books, and that's what I used personally. It wasn't until much later that I even knew this existed. And then I read it and I said, holy cow, this one here, this is a great book for writing your own CPM BIOS. And I went back to it in this project because this project with an SD card works very differently than it does on an 8-inch floppy, which is the one that I wrote so many years ago. I gotta think of it. Was it 30 or 40 years ago? Unfortunately, I'm sad to say it was 40 years ago. Wow. Anyway, I wish I would have read this book first, is all I'm saying, okay? When I referred back to it recently, I noticed that this covers everything very nicely, very well, except for one thing. And that is certain subtle details about how the file system works in CPM 2.2. He's got a lot of it in here, but not all of it. And in fact, I would go as far as to say, and please correct me, I beg of you, and point out that I'm wrong when I say that absolutely no one has written a decent document on how the file system works when you have more than one extent in a single directory entry. I had to figure it out by kind of some trial and error. When we get there, I'll give you the details. It won't be today, but I'm looking ahead here a little bit. This guy right here, Andy Johnson-Laird, this book right here, in acceptable condition for $50. Actually, this is a pretty good price. Quite often you see it for $100. This is, of course, out of print, so the only thing you can do is look for it on eBay. The Leventhal books, I think, are also out of print. I look at my shelf right behind the microphone, and I can see I got all the Leventhal books in view. The only ones I can see are 6502 for whatever reason. But yeah, the Z80 ones in here, these are good too. The difference between this and the reference manual stuff is that he has a lot of diagrams with, he showing you the memory bytes and the arrows where they come out of memory and which registers are in use and all that. While the Z80 reference manual, the user guide, assembly language reference user guide from Zilog, gives you, a narrative, a text narrative of it. If you want more, is my point, this is the one. You could do probably, in my opinion, no better than these Leventhal books right here for Z80, okay? Yeah, and the same thing, by far, this is a light year ahead of anything else, including the Digital Research's own documentation. All right, so if you want something, there's your books, okay? All right, sorry for that digression. Why did I get on that digression? Because this code right here I think is pretty darn elegant, and I know I stole it from one of those two books. Anyway, or one of those two authors, I should say. So what is this thing really doing? I put S. I called it that because it stands for inline put string. Notice it does some stuff in here, and then it calls put S loop. So let's look at this one after we look at the guy that has put S loop in it. What does this do? Write a null terminated string starring a string. Maybe I should fix that spelling error while we're poking around. Null terminated string starting at the address in the HL register pair to the console. This will clobber A, F, and C registers. All right, I went through one of the things why it took me so long to get a video posted this week is because I had to go through my doc and make sure that I wasn't lying about this. I'm probably 90% accurate, so be very careful. Unless you can obviously see what's really going on in here and confirm this. Right now, these may not be rock solid, life threatening guarantees here. I welcome pull requests to fix if I'm wrong. Definitely post some comments on GitHub if that's the case. Okay, very much welcome this stuff. Okay, so this is put S versus I put S. Okay, this one's inline, and this was regular put S. How does this thing work? What this thing is going to do is I don't want to clobber too many registers, so this is going to clobber A, F, and C. I'm going to save the HL register. I'm going to call put S loop. I'm going to restore the HL register, go back to the caller. So what does this thing really do? What it's going to do is one at a time, it's going to grab a character from memory at the address in HL. I'm going to ask, is it 0? If it is 0, I'm going to say I'm done, and I'm going to just simply return back from this loop, okay? If it's not 0, I want to print it. So put it in the C register, send it over to the console, advance the pointer to the next byte to be printed, and go back up here and do it again. All right, so that's what this loop here does. And it's called there because for whatever reason, I probably call it a lot. And for whatever reason, I wanted to save the HL register that's pointing at the starting address of the string, which, as I think about it out loud, I don't know why that would be so important to me, but it was. So I put in this saving of the context in here. All right. So put S loop. One character at a time is printed from memory at the address in the HL register until it reaches a null. This is, in a C program, right? A null terminated string, which is written to the console. And that's really what put S does in the standard C library. Now, what is I put S going to do? It executes an instruction that we haven't really talked about. What this does is one of these exchange instructions. So what it's going to do is it's going to exchange the value that's at the top of the stack right now with the value that's in the HL register pair. So what's at the stack, at the top of the stack when this instruction is executed? Is the return address that was pushed into the stack by the call instruction that we would have expected was used to call this subroutine. And that return address is pointing at the byte in memory after the instruction of the call address. That's where you need to go back to, right? The instruction after the call. So what I'm doing is whatever's in HL, I put into the stack, and it will overwrite that return address. And at the same time, I'm going to put that return address into the HL register pair. Okay? So I haven't modified anything. They're both intact. This is probably why I needed to save the HL register now when I think about it. Okay, so once that's done, I call put S loop. So what does that mean? What it means is, the comment over here says, look, the HL register is the address of the string that's going to be printed. Well, as we'll see in a minute, I oftentimes will put I puts S in there. I'll call that subroutine. The very next thing after the call, I'll just say define byte and put a giant string right there in the middle of the executable code with a null after it, of course, because put S loop prints until it reaches a null, right? Then when put S loop comes back, it will have advanced the HL register along, and when it's done, HL register will have the address of the null byte that caused this thing here to go down to the done routine, the done label here, which causes it to return back up to here, okay? At which point I add one to the HL register, which moves it to the character after the null. Now I'm going to exchange back again. So what did I just do? I am going to take the HL register and put it back in the stack where the return address is supposed to be to go back to when my subroutine is done. So I changed that value. And what was in there, remember, was the old HL register value before this was even called. I don't even know what it was. I don't care, but that'll go back into the HL register pair. So this whole routine here will effectively move the return address from the beginning of the string that I want to print to the instruction that comes after the null that's at the end of the string. So as an example, here's one of the uses that I've done here, right? So here's some code. I call I put S. Here's my byte string right here. It ends in a null character. Just stick it right in the middle of your code. And the very first byte after that is whatever the instruction I really want to come back to when I put S is done, which is this halt loop. In this particular case, I say, hey, I'm done now, and then I end. So that's what's in put S. The SD card we'll get to later on. We already talked about this. Big news for this one is the SPI.asm file. Now, as this doc line right here says, which probably doesn't belong in this particular file, this should probably all go into the SD card library. This used to be one big file, and I factored it into two pieces, get rid of the SPI, put the SPI stuff in its own file. But unfortunately, some of the doc is lingering here, but it's still relevant. It's a foreshadowing. We need to talk about SPI because we're going to use SPI to talk to the SD card. Now, SD cards can use different protocols and different ways of working, but the arguably one of the easiest ways to do it is to talk to it using what's called the SPI protocol. And if you go to the Wikipedia page for SPI, you'll find out this was made in 1979, 43 years ago. So at least something's older than my first attempt at tinkering with CP/M. And it works like this diagram shows right here. So what do we got here? We got the SPI clock, right? This is the host. This is your Z80 Retro board, and this is the SD card in this scenario here, all right? So the clock comes from the Retro board. MOSI, which stands for master out, let's call it SD card in, okay? So this comes out of the Retro board and into the SD card. This is your serial data, the transmit data from the Retro board to the SD card. We're going to use this to send commands down and data when we want to store data in our SD card. This line down here, master in, SD card out, this is the serial data, 1 bit at a time, coming back from the SD card, all right? This down here, the select line, lets the SD card know when the host wants to send data or receive data back, all right? These 4 lines are the signals that we care about the most. Now, if you don't know anything about SPI, it's probably a pretty darn good walkthrough of this. I noticed, I think last year, like 6 months ago or so, Ben Eater did a piece on SPI. Go ahead, I'll put a link in the description below this video. Go ahead and just give that one an eyeball if you need a refresher or something like that. The short of it is, you got serial transmit, serial receive, you got a clock, so it's synchronized to that clock. It's not like like a UART or something like that, okay? It is synchronized. And what do they got down here? They go on and on. They talk, here's how this thing works, sending data, data comes over, data comes back. And then this is a pretty standard diagram you see all over the place. You have these options. Does the clock go up when you're sending data, or does it go down? What's the polarity of the clock? And this has to do with which mode you're using. That's why we need to make sure we all understand. Well, I'm in mode 0, which means polarity is 0, which means this top row is the one we're looking at. SS means it goes low when we want the SD card to communicate with the Retro board, or vice versa. Okay, the clock phase equal to 0. This is the way the data transitions line up relative to the clock edges. This is phase 1. We're using phase 0. All right, so just be aware that there's different ways to use SPI interfaces. So if you get confused, I'm in polarity 0, phase 0. That's what mode 0 really means, okay? So let's open that up in Vim. Maybe the font's a little bit bigger and fancy in color and stuff like that. Library, SPI.asm. All right, so this is the guts of what we want to talk about today. SD card library. Here's the waveform that you just looked at with all the extra noise removed. This is the one we want to look at. So as you can see, the relative alignment and interactivity that we're shooting at here. Okay, a big picture here. We only care about the SD cards, okay? Keep that in mind. They all operate in mode 0, which is this diagram right here, which means that whenever the clock has a falling edge, like this, and like that, and like that, that's when the bits on these serial lines change. So no one's watching at that time. It's transitioning. On these rising edges, that's when both the Retro board and the SD card will take a look at the value on MOSI and MISO and transfer a bit, 1 bit, between each other. Now, the other thing about the SD cards is it'll always communicate in a multiple of 8 bits. So what I've done is I've written some routines down here, and that's what we're going to look at here in a second, that send a multiple of 8-bit values back and forth on the SPI part, okay? So it's an integral number of bytes is what that is, okay? So what we're going to do is we're going to send data from the host to the SD card, Basically, that's what MOSI does. And we're going to send data from the SD card back to the host on this one on Meso. And what we need to be able to do is we're going to move the SSEL low. Okay, when it's low, this starts happening, right? We're going to see the clock tick up from low to high to exchange the first bit. And that goes both directions at the same time. All right, don't forget that. It just so happens that the SD card has kind of a half duplex view of how things work. But be careful. Don't think that no one's looking at the data over here when the SD card is sending data back over there, because there's times when that's not necessarily true. So you have to be very cautious about sending noise, is my point, on this signal here from the Retro down to the SD card when you're reading a response message back from the SD card. Okay, during those time periods, as you can see, I drew that here as a high signal. So what I want to do is anytime I'm just clocking along here, waiting for the SD card to send me something, I want to keep MOSI high, okay? Because it turns out that there is a way to signal the SD card when MOSI goes low. But if MOSI's high, when you're reading a response back from the SD card, or you're waiting for a response from the SD card, which is the critical one we'll see in a little while, which is the critical one that we'll see when we talk closely about the SD card driver, that's when you do not want MOSI up here going up and down at all. You want to keep it high all the time when you're simply reading, when you're clocking for the sake of getting data from the SD card. You might think it doesn't matter because no one should be looking, but they are, okay? So I bring all that up now because that's where we're heading, and therefore these routines are written in a certain way to make sure that this is true and stays true, all right? Okay, so SSEL goes low. We send a multiple of 8 clocks, 8, 16, whatever, and we can exchange a bunch of data bytes, or bits, I should say, with the SD card on these lines down here, all right? So the first thing we need to be able to do, arguably, we need to be able to control the SSEL signal, and we need to control the clock. So what I'm going to do is I'm going to fire up a test app that's just going to tinker around with these pins, just to sanity check it. And we'll get 2 things out of it. 1, we'll make sure that we can change their values. And 2, we're going to see just how fast we can make this thing go. Because this is going to throttle our total performance while we're communicating with the SD card. And we're going to see that, while it's not very fast, okay, it turns out that it is on the order of a single density floppy disk back in the day. So when we're talking to the SD card on the Retro board, this is the real deal. This is how and in fact, I would even argue this is going to go much faster than what floppy disks did back in the day. Because at exchanging the data at about the same bit rate that they used back in the day, you would argue it's the same, but not really, because when we get to talking about the BIOS and sector translations and skew and all this other fun stuff, the instantaneous rate of data coming off a floppy disk matches that of the SD card driver we're about to look at here. But you have a huge amount of time waiting for the disk to go around in circles for the sector you want to read to line up with the head. And those delays are enormous compared to what you get with the SD card, which essentially is always ready immediately. As soon as I say, I want to read some data, it immediately sends it out. I don't have to wait for a disk to go all the way around in a circle to find it. I also don't have to move the head in and out, which is even slower than the amount of time it takes the disk to spin around. So this actually is pretty fast if you're used to 8-inch or 5 1/4-inch floppies on, you know, your old Scissor or K-Pro or something from back in the day. So let's look at our little test app first. Why? Because I've been preparing this so long, I can't remember what comes in what order. We've seen all this startup before. This is the app that we're going to run. This is the app that we're going to evolve into the bootloader. Okay, so the first thing we're going to do is going to fire up the SD card, see if it can say hello. All right, then we're going to try and get it to send data and all this other fun stuff. So let's just get the SPI to work. Where are we at? Usually we've seen all this before. Load the stack with 0, let it wrap around to the top of memory, put this code starting at 0 because it's going to go in the flash, and that's where the Z80 goes when it boots up. Copy the code out of the flash into the RAM, then shut the flash off, run out of the RAM. Here's where we set up our stack. This is setting up the CTC the way I discussed it before. This is going to set up the SIO. And because I set the CTC up with the divide by 6, it turns out I can use J11A that I showed you a minute ago to select between 115.2 and 19.2 if I start it like this. And I have the oscillator in there that I specified in the schematic. All right. So I just fire it up like this all the time, and whether I need it or not, because the CTC port 1 is otherwise not used anyway, it doesn't matter whether I configure it or not. And if I do want to run at 19.2, I have it always ready to go. So this is kind of a handy. This is kind of my standard way of starting it up now. What am I going to do? We just looked at this. I'm going to send a boot message. I'm going to print it out. I'm going to call this to print a blank line. Why I didn't just put a blank line at the end of that, I don't know. I probably had some other code in here earlier, and it ended up looking like this. And then I got all these little test routines. So this first one's going to send 80 clock signals down the clock port. So let's turn that one on. That's where we're shooting for this one right now. What's wrong with this? I didn't edit the file. There we go. All this is commented out, and then it'll say test done, and then go into a spin loop. Let's look and see how I compile this. All right. This is a little technique. Back when Apache first came out, and they might still do this for all I know. Maybe, maybe not. So give credit where credit's due. This might be a Rob McCoolism. I don't know. He's a guy that was at NCSA when they first wrote up, Mosaic and the web server that became known as Apache. Anyway, they have a technique in their config files where they put at, and then they kind of made a sort of a variable name and I said, that's not a bad idea. So I use it to this day. It's unlikely that you'll ever see at something at in any file. So this is a relatively benign thing to put in a file, and at date is another one. These are going to be symbolically substituted into. Now, if you have a good assembler that has, a preprocessor and macros that are like the C preprocessor has, then you don't do this. But when you don't have a good assembler that's all super fancy like that, here's my way of doing this. So let's look at this a little bit. This is the boot message that's going to get printed before it runs these test routines and then says it's done, all right? So what is it going to do? It's going to say retro board, yada, 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 and it's going to keep printing until it gets to this null down here. So it's going to need to print this and that. What is this for? Now, I like doing this a lot when I do my projects. I almost always do it. What I want to know is what's the version of the Git repo that was used when this program was compiled, and exactly what's the date that the program was compiled on. Okay? That way, anytime I watch this thing boot, it prints up a message. I know, if it's an old version, a new one, you're a fool to do anything else. I'm a fool to do anything else, all right? Let's look and see how this works, because this is not overwhelmingly obvious. Maybe it is. Not always, okay? So here's the assembler we're using. It's Z80 ASM, and this is a very crude, basic assembler. Super simple. That's why we have to do some of this stuff on our own. Z80 ASM is capable of looking for files, and we call it an include path. If you say capital I and say, if I said include sio.asm and it's not in the current directory, don't give me an error. Look over here to see if it's over there, and /lib, which is, up one directory and over in the library. All right. And you can see that $ASM flags is sitting right down here. So here's where I set it. And then I could tweak it around. And the reason I use this technique is as if I move it around, I might actually just comment this out and leave it there for reference, and then have another statement below it for a different one and stuff like that. So project management type of thing there. The all rule in a make file is, a de facto standard for, when you type make, what's kind of like the default rule. All is not the default rule, okay? The first rule that make finds is the default rule. And almost everyone likes to call it all. So I'm going with the flow here. So what does that mean? All. That means tell make to generate this file right here. Figure out how to do it and make it so. Okay, now what make is going to do is going to look around a little bit. And first it's going to see, does that file already exist? And the answer is no, because it needs to be assembled from the SPI test.asm file, which is sitting right here. Okay. So it says, I don't know, I don't have it. How do I make it? It's going to look around and say, look, I have this is how you specify a rule. I can convert an ASM something or other. This is, a wild card. Something.asm can be converted into the same thing.bin by doing this. Aha. Okay. So this is the rule, the recipe, some people like to say, on how to create a binary from an ASM file. All right. So it knows it needs to do that. It looks around and goes, oh, I do believe I can use this rule. Okay. So I'll just do this and hope that what I want will show up. And if I write the make file right, it will. Okay. So what does this thing do? Not the cleanest thing ever, but cat means to just copy a file that's listed here and print it on what we call standard out. And this pipe means take standard out, and rather than printing it on the display, make it the input to this command here as if I typed it in on the keyboard. Okay, so less than sign is a variable that's, remember this is a recipe, and I can use this no matter what it is. xyz.asm, abc.asm. I don't know the name of the file. It's something.asm. So I don't know what the name of the file is. So make gives me this $less than sign variable and says, I'm going to help you out. When this thing runs, I'm going to set $less than equal to whatever this thing is that make has decided to employ this rule, why it's doing this. All right, so this would be in my case it would be SPI test.asm would be showing up in here. So this is going to cat out the source file here. All right, and then it's going to run this stream editor, the sed command. And now you know why we're looking in here at these things. So where do these come from and what's going on here? Stream editor, I use it in the simplest form. You say s/this/something else/g. What this thing means in my mind, what I think of it, right or wrong, s means substitute all occurrences of this text string in the input, which is standard in from the file, to whatever this is, and g means globally. What that means is don't stop on the first one. Keep going if there's many in the file. All right. So I'm going to change date to whatever this is, and it will be set up here. We'll look at that in a second. Then when that's done, it's going to change this to whatever this is, and you can see it comes from here. And we'll look at this in a second. All right. And then when all that's done, take what the resulting mess is and pipe that into Z80 ASM. Dash means assemble whatever you're given from standard in. Put the output in $at, which is the magic makefile magical rule that represents what this is supposed to be. And I say double minus list equals base name, blah, 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 blah. This says I want a listing output file, but Z80 ASM is a little annoying. It doesn't really help me in this capacity. I really need to name it something. So I'm kind of in trouble here. I have to use another fancy thing here and say I want it to be the same name as the .asm file, but I want you to remove the ASM. So that's what base name is doing. And then change it to LST. So it converts the ASM into a bin, and this byproduct will be that it also is going to create a something or other .list. All right, so that's what this whole thing does. if you wondered, as you've seen this before, but I never really described it. So let's see what this is going on up here. If I say date, this is me assigning a value, which is from this expression over here to some variable called date. The same thing, assign some big blob over here to the variable called get version. These are make variables, therefore you can use them, substitute them in here with dollar open parenthesis and put the name in there. All right, so this is all make stuff. You can go read about GNU Make. The manual's pretty good, but it's a reference manual style thing. If you're not happy with Z80 assembler from reference manual, this might even be worse, but that's how I learned it. So FYI, I know it can be done if you give it a couple of weeks of tinkering. Okay, so what's going on here? Basically, it means run this command and take whatever this thing prints on the screen and store it in this variable and use it here. And this says run this command, and then the semicolon says then run the other one and take the output of both of these commands and put it in here. So what's the takeaway? Whatever this is gets put in that date at thingy in the boot up start. Hello, I was compiled on this date. That's where that comes from. This one down here says here's the git repo version number. And I use a couple of commands in here asking Git to tell me about the state of the repo. And Git describe long form, and dirty means if it is not committed. If I made local changes to files since the last time I committed it, pushed it out, put a little dirty on there to let me know that this is not really the same thing that is in the repo. It's some repo version, but it has been modified. All right. Again, I want to know, can I reproduce the source code that was used when I built my project? This down here is going to give me a string that represents the last time and the date that I committed this version into the Git repo. So let's look at this. I'm going to burn up so much time. This could be the whole darn video in itself. Bear with me, folks. Okay, so here's what it means to say date double minus RFC 3339 in seconds. This is an almost ISO looking date. Year, month, day, hour, minute, second, minus your offset from Greenwich Mean Time. What does this thing do? This is describe this. So it says it's dirty, and we'll look at why that is in a minute. And then we can look at this, and this is another date, but this is the date that I last did a commit. So at 4:11 this afternoon, it's currently a little later than that. It's 6 o'clock for crying out loud. So like about 2 hours ago, give or take, I committed stuff into my Git repo. And now that's what this time is. It is, 2 hours later. This down here means that this is the actual repo version that I'm using right now. And this says somebody touched a file. So if I type git status, I modified this file here. I have some other files in this directory that aren't part of the repo. This is my tinkering around getting ready to make my BIOS and my CPM image that I'll push up later on. So that's why this says untracked. These don't count, but this one does. And by now, hopefully, you've taken some time to figure out how to use Git. And I can say, what did I do? What did I do? You saw me do it. I removed the comment on the 80 clock. So this is the dirty thing. All right. So that's everything there is to know, hopefully, about this make file. And when I type make, you can see this thing actually run, and you can see the substitution going on. This is right now. That's when I just typed make and compiled it. The Git version is this thing here, and this time over there is the time that represents this Git version here. If you don't know how to read that, if I type git log and I look at this, see where this says commit right here, see this yada 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 yada, and it ends with the F4. That is a short form of this number right here. This is version 0.1-19/G, and then this number right there is part of this hash value that represents this very specific version that I can recreate at any time. The rest of the junk you read in here, this is 19 commits after the last time I tagged the repo at version 0.1. If I type git tag, what is it? This will tell me all the tags in there, and there's like a git tag long or something. I don't know. I don't know. You go read a Git reference manual for all the little details. The point is that when you compile this thing, it stamps it with the time you compile it, the version of the Git repo, and the time that the Git repo was last pushed up. So you can see the other substitution going on over here. It says save the file output in SPI test.list, and if you need something, it's over here. All right, so that's my make file. We never really looked at these. While I'm on a roll, let's look at one of them. The listing file, most assemblers basically kind of do the same thing. The idea here is it's going to save to a listing output file, the source code on the right here, and on the left it's going to show you all these instructions. Compiled, call, SPI read8. What does that mean? It's a CD8002. There's the binary. These are hex bytes that represent this instruction. Okay, what else does it do? Well, this particular assembler says, hey, this is file dash. And remember, when I compiled it, I said compile from input dash, which means it read from standard in. So this is what it got from the sed command after the substitution was done. And we all recognize this. And the next line after that is include io.asm. And this is where it gets interesting, because it's including IOASM. This is io.asm right now. If you look at the LST file, this is what really got assembled in the exact order in which it's assembled. So as we get into hairier versions of code and complicated things, you may want to be looking at these to make sure you know what's really happening. Did it get the right include file? Is it reading the wrong one? Maybe it didn't include it at all. All kinds of weird things can happen. All the answers are in the LST file, okay? So over here it says end of file io.asm. So this is what happens every time you say include something. You can see the include right there, because that's part of your source code that it normally prints out, followed by the contents of that file. And when it's done, it'll mark, by the way, this is the end of the file you just included, and now we're back into the main reading of the input, okay? And again, there you go, stack top 0, start using the address of 0 as the address of where all these bytes go. And you can see 382604, that's this instruction, and so on, all right? So we go along down here. We should be able to see all kinds of fun stuff. Load stack P, comma stack top. Remember that was set to 0, so 31 must be load stack pointer. And there's the zeros, okay? Here's the program that we wrote. He's going to call test 80 clocks, go into his fun little loop. And why are we in here? Look, there's our little substitution. All right, so when he prints this message out, I now see git blah, 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 blah. And by the way, it's dirty, which, it's not a clean commit. And it was last committed here. Here's the time it was compiled. All right. So that's what the LST files are all about. Let's go back to ASM here and make this thing go. Watch this happen on the clock, on the scope rather. All right. So what we're doing, where's my code here? Get my wits going here. Okay, test 80 clocks. Print a message, test 80 clocks, and then stop. Okay. Let's search for this label. It's in this same file below. That one was commented out. Here's the actual code. What's he going to do? Load B with 10. Then he's going to call SPI read8, and then he's going to go back up here. DJNZ means decrement B, subtract 1 from B, and if it is not 0, go back up to this label here. So what this is going to do is it's going to call SPI read8 10 in decimal times, and when it's done, it's going to return. So let's look and see what's up with SPI read8. There's two ways to do that. You can look at the listing file if you want, but it's kind of indented over and it might not fit in this giant font that I put on these recordings, so you can actually watch these if you want on your phone. That's actually one of the ways I test it. If I can see it on my phone, anybody should be able to see it. Okay, so here's the SPI stuff in here. If I type it in right. So here is the SPI driver where we started, right? So what did I do? I called read8. Let's look at read8. Read8 is right here. All right. little note to myself as we evolve. If you see a XXX comment in my code anywhere, you want to look at those first. If something doesn't work, I will disclose my own dubious choices by putting XXX something, something, something in there. And this is very common. You see it all over the place. I'm not the one who invented it, but it's a great idea. If there's something that should be done in this particular case, this is a performance thing. This is me disclosing that I'm a lazy oaf, and this might run faster if I took this and stuck it somewhere else. But we'll get there later, okay? Keep it simple for your first draft. What does SPI Read 8 do? It puts 0 into the E register. Why don't we read the doc first? This whole thing, the motive for this is to read in 1 byte, 8 bits, from the SPI port and return it in the accumulator, right? So what does it say here? Mosey will be set to 1 during all the bit transfers. So that goes back to my comments earlier. Make sure that it does this when you're talking to the SD card and you don't care what's being sent to the SD card. Set it to 1. When this code is done, it will leave the clock output set to 1, and Mosey will be set to 1. It'll destroy the contents of these registers, and it'll return the byte that was read in the accumulator. And by the way, it'll also, by coincidence, happen to also be in the E register. Again, I added this comment because I happen to know I was writing some other code and taking advantage of this fact. So by adding it to this comment, it's a note to you, me, anybody who wants to modify this code, that this is an advertised feature. It is part of the contract that anybody that calls this routine can count on this being true. Okay? So that's why that's in there. Okay, so what does this have to do with the clock? Well, because the Mosey will be set to 1, and the clock will tick once for each bit that needs to be transferred, this is how I'm going to test my clock ticking, all right? It may or may not be a great way to test this code here, but for sure, it'll test to make sure that this code can tick the clock. So let's see what this thing is doing. With all this in mind, let's see what happens. So SPI Read 8 comes in right here. Put 0 into E. This is going to accumulate all the bits that it's reading in. I'm going to read it in and shift them into the E register. This is going to be my working data variable that's going to accumulate those bits as they arrive. And what's he going to do here? He's going to load the accumulator with a GPIO output cache. Now remember, the GP output port is used for more than just the memory bank. It's used for the printer strobe signal, and it's also used for these 3 bits to talk to the SD card. It's absolutely critical that you don't change the value of these 4 bits here inadvertently, because, as we talked earlier, it'll pull the RAM out from under your feet. Okay, so it's absolutely critical. If you want to change the value of the clock or the MOSI or the SSEL pin or something, what you need to do is make sure that you have to write all 8 bits due to the way the hardware is designed here. You have to make sure that you write the same value that was in all these pins before back out for these values while you're tinkering around with these 3 up here, all right? And that's the point of this. I explained that before, early on, when we were talking about all the different variants and the flash and all that other fun stuff in this series, okay? So here's us using it for real now. Grab the current value so we don't mess up, basically, the memory bank number. Then what am I doing? I'm going to AND it with tilde SD clock. I'm going to make the clock 0. I'm going to take whatever's in there, regardless of what's there, and make sure that the clock bit in the value in the accumulator, that's what this thing does here, is 0, is tilde a bunch of binary. This only has 1 bit set in it, and it's the SD clock bit, which would be this one right here. So if we look in the io.asm, then this will be set to 2, right? Because it's 1, 2, 4, 8, and so on in terms of like a hex value, okay? So tilde hexadecimal 02 means a 1 and 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 a 1, and there's a 0 there. So when you AND that all ones but a single 0 bit for the clock, then you're going to end up ensuring the clock is 0, right? Okay, so then what I'm going to do, I'm going to OR in the same logic, but I'm going to use an OR, which makes sure that regardless of what it was before, the Mosey bit in the accumulator will be a 1, and then I'm going to take that whole thing and stick it in the D register. Then I'm going to call this. What the heck's going on here? I did talk about macros before. Macro introduction. SPI read 1 here, it looks like an instruction mnemonic. But what it really is, the assembler looks in there and says, I don't recognize that as an instruction mnemonic. So it could be something else. Well, one of the other things it could be is a macro. Here's how you define a macro. What a macro is you say, look, I just want to not type all these instructions in 50 times, okay? In this case, 8. So I'm going to create a macro called read 1, and every time you have like something that looks like an instruction to the assembler called read 1, just put all this code in here and read and assemble this, okay? And if you look in the LST file, you'll see the macro, and then you'll see it expanded, we say, 8 times down here, all right? And the reason I did it was because it took me a long time to debug this is why. And I don't want to have to edit it 8 times. So I want to make sure the exact same code appears 8 times. That's why one of the reasons we do macros. You'll see another reason in the write routine above. Okay, so what are we doing here? We load A with D. Now this macro assumes that this was done before it got here. So what's in D right now? What's in D is the current value of the output cache with clock set to 0 and Mosey set to 1. That's what's in D when this here expands into this here. All right. So I put that in the accumulator and I write that in the output port. And as a result of that, at this point in time, I know that the clock is at 0. If it wasn't already low, it is now. Okay, we also know that Mosey is 1 because that's also output in that same thing. I should maybe add a comment here. It doesn't really matter because it's in the comment above here, and we just talked about that. Okay, so what happens now? I take the value in the accumulator and I OR the clock bit into it, which causes it to be a 1, and I output it again. That rising edge is the indication to the SD card that we're now reading, sampling the input. Okay, so the next thing we do is we read from our GPIO in port, which, as you might recall, is this thing over here. And one of the bits in here is our meso bit. Now, the code that I wrote there takes advantage of the fact that this is the most significant bit in this port. All right, there's an optimization that is based solely on this absolute fact in that code. All right, so it's not a general purpose code. It's written very specifically for this schematic. So if you redrew this and I don't want to route, maybe there was a trace that was in your way and you moved it over here, you need to rethink what's going on. All right. This one knows that meso is in bit, the most significant bit when this takes place. All right. And by that, I mean what happens down here. So I'm going to read it in. I'm going to AND the accumulator with this. So all the bits in the accumulator become 0 except for the meso bit. So that means at this point, the accumulator will either equal 0 or it will actually equal that value right there, which means there will be a 1 in the most significant bit. I then OR the accumulator with E, which the first time through here it's set to 0. But remember, E is the thing that collects all the bits that we have seen so far. So that means the very first bit is now in the most significant bit position in the E register, or rather, I should say in the accumulator. So that means at this point, what we have is the current bit is in the most significant bit of the accumulator, and any other bits that have been read in so far, and the other bit positions in the E register are also in their respective locations in the accumulator. When I'm done with that, I'm going to do rotate left, carry A. What this is going to do is it's a rotate, and I don't know why they put the C in there, because it rotates without going through the carry. What this thing is going to do is it's going to take the most significant bit that we just read in, and it's going to put it into the least significant bit position in the accumulator. And all the other bits that were in the accumulator that came from the E will all move to the left one. Okay? When I'm done with all that fun stuff, I'm going to stick it back in E so that I have it next time I go through this, right? So look what's going on here. I just call this thing as it is 8 times. So what's going to happen is, if you think about it, each time it goes through here, it reads in one bit to the most significant position in the accumulator, and then it moves it around to the least significant bit and keeps moving everything to the left. Now, up here, there should be a statement saying that remember that the maybe it's in the SD card library. It so happens that when the bits are transferred into the SD card and out of the SD card, the most significant bit is transferred first and the least significant bit is last. So that's why it's very important when you look at the logic in here, that the very first bit that's read in the first time through, the expansion of this macro, that by the time we're done, it needs to end up in the most significant bit. And it will, right? Because the first time through, it actually is read into the most significant bit, and then it's ORed with E, which is 0. So the only thing in the accumulator, and the very first time this goes through, is the most significant bit. It will be set to what it's supposed to be. I then do this and move it over to the least significant bit, okay? And then each additional bit that comes along, it keeps doing this, and it does it 8 times. So what happens is the first one goes all the way around and ends up back in the most significant bit when everything's done. All right, it's just a coincidence. I'd like to say I planned it all out that way, but I didn't. It was an accident. It turned out to be very fortunate, and by that I mean that I put the meso bit in bit position, the most significant bit position in that I/O port. Okay, so when this is all done and it happens 8 times, all the bits go around and they end up where they're supposed to be. Okay, and that's what happens for reading 8. Now we're going to use this just to watch the clock go. We're going to throw away the value in the assembler and the accumulator rather when we're done. But this is a very convenient way to just clock the clock while Mosey is 1. All right, we don't really care about this when we're ticking the clock. What we care about is that we set it low and then high. We can play around, yeah, that's fine, but for this particular test, what we're doing is we're making sure this part of it works and that the thing just doesn't crash. All right? So let's compile it up. And in my I usually have a README file, and I keep this in here so I can just cut and paste it. The idea is that if you do what I do, then this will work for you. I'm on my Raspberry Pi, which has my Flash programmer, and if I look at my home directory, I got a bunch of stuff in here. One of them is the programmer source code that I cloned out of GitHub before Christmas. I haven't touched this in a while, and that is where the Flash programmer is. So if I just run it like this, I will send out this particular test program on my retro board. Okay, so let me bring in this terminal. This is plugged in. It's set to 19.2, and my J11 is in the right place for that. So, and then my windows are going to get messed up when I cut and paste. Hang on a second here. So I'm going to paste this in. It's going to do its thing, and it's already done. Okay. It's usual, the Flash download took place, and you've seen that before. And when this thing fired up, it printed out that message that you saw, and here's the git repo and all that. It's super awesome. Hello, I'm the library tester, and then it says nothing followed by tests done, because that's what the clock doesn't print anything. So let's run it again. You can just hit reset on the retro, and we can see what comes out of the oscilloscope. So here's how I hooked up the scope. This is the trace we're looking at. It's in this middle pin. That's kind of glary there. If you look closely, it says clock. And I use this pin over here for my ground. And here's what happens when we run the app there. All right, so I'm triggering what? Probably on the rising edge here. And you can see what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groupings of 8 clocks each. If we zoom in a lot, we can probably count them. 1, 2, 3, 4, 5, 6, 7, 8. All right, now the reason they're in these groupings is because when the code runs, remember we're bit banging this. This is the rate, the amount of time it takes to go in there and to go, set the clock high, low, when it's in that inner loop, and it returns from the subroutine. It goes DJNZ back to the top of the loop, calls the subroutine again, does 8, and so on. Now, if we zoom in a lot with the scope, we can actually see how fast this is really going. It's going to run at 156 kilohertz, which is just a shade faster than single density 5 1/4 floppy on, your old TRS-80s. And just for fun, when we take a look at the gap between here is a little longer. This is where it's returning from the subroutine and come back and in. All right, so I'd say that's a successful test here, all right? Let's move on to this other one here, the SSEL pin. You might think that this was easier because all you need to do is move the SSEL up and down, but that's not quite true because in the context of the SD card, whenever we move the SSEL up and down, we're also going to mess around with some clocks, as you'll see in a minute. Now, arguably, these probably should not be in the SPI level, the bottom level of the driver. I probably should refactor this out and put it in the SD library. It should be easy to do. Let me know in the comments below what you think is a good idea or not, or whatever. Maybe you don't care. I don't know. Or, hey, pull requests are always welcome. So let's go up here and mess around with that. So we don't want to do the 80 clocks. Let's just see if SSEL going on and off will work. And as I alluded to, these two here, I'm going to set it to true, and then I'm going to set it to false. And remember, it's active low. So true means to move it down, and false means move it back up again. Let's go back and look at these programs and see what those things do, which is back in the library. Come on, where is it? That one right there. So let's search for that. Here we go, SSEL false. First, we're going to set it to true. Let me open this in Vim. And then we get all the fancy highlighting in the colors. Don't ever tell anybody I said that. I'm not a huge fan of this all the time, but it's all right. So here's SSEL true. I guess it's not a big deal. All we're getting now are parentheses. Okay, for naught. What do we got here? Assert the select line, and FYI, this will leave SSEL set to 0, which is asserted, which is true. It'll set the clock to 0, and Mosey will be 1. Remember, we always want to keep Mosey high whenever we're not using it for something else. Okay, I can't stress that enough where we're going with all this. So what do we do here? We save DE, and then we're going to pop it back down here when we're done because we're going to mess with it. And this code is written so that, hopefully, when all the smoke is cleared, that the accumulator will be the only thing that has been modified. So what is he going to do? He's going to call SPI read 8. That's why we did the clocks first, okay? So he's going to call SPI read 8. Why? Because in an SD card, what happens is the card is idle when you're not sending a clock down to it, and it goes into low power standby. And the manufacturer wants to make sure that you can, account for all kinds of different possibilities. And if it goes in a low power standby when the clock is not running, it won't be awake to see the SSEL line go active. So we need to send some clocks down there. So by reading 8 bytes from it, before we change the state of the SSEL signal, which happens down here, that'll wake up the card. Okay? So that's the whole reason we do this. We're going to read in 8 bytes, throw them away, and it's going to do what we just saw. Send some clocks down there. When that's done, we're going to get the value in the output cache for the GP output port. We're going to make sure that the clock is low, Mosey is high, and we're going to output that value. And we're going to do that before we make SSEL 0 or true. And the reason we want to do that is because we don't want the clock to glitch after the fact. We need to know it's already 0. And we want to make sure Mosey is already 1 if it's not already in that state, so that when the SD card wakes up, all will be well. Okay? One could argue I probably should have done this before I did the read 8. Maybe that's a good idea. It just so happens that it doesn't matter until SSEL is true. Okay? The real critical thing is don't mess around with clock and Mosey after you assert SSEL. Okay? All right, so those are in the right state, and then we're going to shut off SSEL and make that low, and we're going to store that back in the cache in this time. And then we're going to do that because of what you saw in read 8 and elsewhere. They start by saying, hey, what's the current value in the cache? And they modify it. All right, so we need to make sure that the value in the cache says clock is 0, Mosey's 1, and SSEL is 0, so that if we're diddling with other bits, these stay in the state that this function leaves them in here, all right? So that's why we save it back in the cache. We then write it into the output port, and when we're done with that, we send it another 8 clock cycles. And we do all this, the clock cycling, because the SD card specification says to do that. And later on, we'll talk about the SD card and where to get the spec and all that other fun stuff. This video is getting too long, so let's just get the SPI stuff going, and then we'll come back at the higher level later. Spoiler alert, the SD card spec has got all these click-through licenses and junk, and you're not supposed to reproduce it in any manner. So I can't really show you the doc here, but I'll certainly tell you what you're supposed to do. It's all over the internet, and you can Google for it and get your own copy, but I really probably shouldn't show it on my channel if they really don't want me to, for whatever reason. Probably because they're actual members that pay a lot of money for it, for the fancy specs that are not free and widely available, want to be protected against something. I don't know. Anyway, so let's go ahead and turn on the, we already did that, the SSEL. We saw what it did down here. Test SSEL will, set it true and then set it back to false. So we just walked through set true. Guess what set false does? The exact same thing, but it's going to send out more clocks or something like that, right? So false. What is this one going to do? Save DE and restore it down here. Why do we save DE? Because the read 8 modifies the DE registers. So again, we're going to send some clocks, then we're going to grab the cache value, which is the one that we just saw before. Make sure that the clock is 0 before we modify SSEL and Mosey to be high. Store it back in the cache, output it. Clock a few more, and then return. Okay, I don't remember if we really need to do 16 here or 8 or what the deal is, but in the spec it always says, when you're done, send some clocks, change the select line, send some more clocks, and when the clocks stop, the SD card will go back into low power standby while we go off and do our other stuff. Okay, so let's go ahead and make this, and we can just rerun the flash command because I just recompiled it. And we reboot it, and which just printed this, and this time it said testing SSEL. All right, let me go ahead and hit reset, and we'll see it go by again. All right, it's too quick for me to scroll the window back in real fast here. All right, so this time I'm going to hook up my scope like this. I'm going to trigger on the card select, or the SS line, right? These labels here match the labels that are on the SparkFun board that I put these header on here for. And these pins are really handy because you can clip your scope on here. But while I'm poking around in here, I notice, be very careful. Remember, this pin right here is 5 volts. If you connect this pin here and short it over to the 5 volt over here, while there's a card plugged in here, the odds of that card surviving are pretty low. So be careful, If you're not going to use this header at all, then you might not even want to solder it in. Don't be tempted. Look at the way I put the scope clip on here. It's clipped down here, and metal goes around the top to stay away from this pin. Of course, there's no card plugged in, so it's not a big risk, but just be careful and beware of that, okay? Cards are 3.3, not going to be happy with 5, okay? So what do we got here? We got a card select. This is my trigger line, and the clock now is on, this is going to be the purple trace that you see. And here you go. There's the select going low, going back high, and there's the clock. So what do we got? We remember the 8 clocks, then go active on SSEL, and then you got another 8 clocks, and then when it says set SSEL back to false again, it sends out 8 clocks, makes it false, which is high in this scenario, and then it does 16. So there's the first 8, and the other 8 are in there too. So scroll it to the left a little bit, and there's the other one, right? So there you go. There's me just turning it on, doing nothing, and then turning it back off. So what's next? Test bits, right? Simple Mosey bit patterns. So let's see if we can actually send out some recognizable bit patterns by sending a few bytes out, all right? So if I just send out bits, well, let's see what this routine does. The problem will be triggering my scope, and my logic analyzer has been busted. Hey, any of you analog video guys out there that want to fix my logic analyzer, I'd really appreciate it. It's just something wrong with the analog part of the scope. It works, but the picture's all messed up, and poked around in there, and I don't know, maybe it needs to be recapped. I don't know. I'm not a high volt video guy. Anyway, what do we got here? Test bits. What does he do? He says he's going to load HL with a buffer address, which is right here. It's got 1, 2, 80, and a 40 in there. These are going to be the 4 bytes that I send out. The SPI Mosey line, and this is going to be the number of bytes to send. Load E with 0. What's going on here? Oh, I'm going to hex dump this out. This is calling the hex dump. No pretty format. And then when I'm done with that, I'm going to say set SSEL to true, which we just saw. Then it's going to say same thing, load HL with a bit test, then 4 bytes for the number to transfer, and call SPI write stir. Guess what that's going to do? It's going to call read 8, or in this case, it's going to do write 8. We'll look at that in a minute, as 4 times, and then we'll set it back to false and return. Okay, so let's go look at write stir and then the write code, and it'll just be the mirror image of reading. There's a little twist in there that we need to make sure we all understand when we're writing. But here's the write string, right? It's going to work just like that put S. It's going to load 1 byte at a time from memory in HL. It'll add 1 to HL. It's going to DJNZ back up here because the B register has the number of bytes in it to send, okay? So as it goes 1 at a time, rather than putting it on the serial port and the SIO to print on the console, I'm going to call SPI write 8, okay? And that's going to be the mirror image of read 8. So let's look and see what's going on in here. Bird's eye view. Oops, scrolling problems. Here's another macro here for each one of the bits. And here's the setup code. And then here's the macro getting used. Okay, so let's look and see what's happening here. I guess we can start with the dock. Right, 8 bits in the C register to the SD card. I should call that the SPI port, because that's what's really going on here, the SPI port. And discard any received data, and this is critically important. Most SPI devices really kind of only work in half duplex mode, and you're either clocking data from the host to the client or the other way around. So, therefore, what's going to happen is I'm going to send data out, but I'm going to just throw away the data that comes in. I'm not going to even bother reading it. I'm going to ignore it, and that's okay with an SD card. It might not always be okay, but remember, this driver really is only designed to deal with SD cards, so this will be fine. It's assumed that the GPIO out cache matches the current state of the GP port, right? And that the SSEL is already low. This will leave the clock high, and the Mosey will be left to whatever the last value is it sent out, which would be the least significant bit of the byte that was written out there, because again, the SD card does the most significant bit first. So let's see what write 8 does. It starts in here. It's kind of the same sort of thing. We load A with the output cache. We're going to still play this game. We're going to kind of like prime up a value in a register and reuse it, because this is going to waste a lot of time if we did this for every single bit, right? So we're going to take the current value, and then this has to be done. Why does this get done? I wanted to do a tilde on all this stuff, and this gets us back to the, well, you get what you pay for. The cheap price of $0 for the assembler that we're using. And again, this is a super simple assembler, and it can be confused and tricked because the Z80 assembly language is a bit of a flaw, in my opinion, because it uses parentheses in some meaningful way, especially when you put parentheses around the HL register or a constant value like it is here. It takes this as an address, and it really goes and it loads the accumulator with a value out of memory at the address that's in these parentheses, okay? And you can kind of trick the assembler into getting confused. If you just put an expression in parentheses, it might treat that as an address and go get a value out of memory. So the quick, easy cheat way is to say 0 plus something if the assembler gets confused. Okay, so if you don't want to load a value out of memory, just put 0 plus some expression in parentheses if there needs to be parentheses here. And I think it's probably the problem came with the tilde. Maybe that didn't work right. I think it has to do with the simplistic logic and how it parses these expressions. Anyway, that's why there's a 0 plus on here. And this is not just this assembler. It didn't take me long to guess to try this to solve this problem. Because this issue shows up in languages all the time that are maybe not well thought out, perhaps. And by that I mean, why didn't they just put square brackets in the language? I mean, they can do anything they want. Then there wouldn't have been a problem with using parentheses in mathematical and Boolean logic expressions that could possibly cause an ambiguous situation. So to de-ambiguize it, 0 plus something makes it definitive. So what is it doing here? It's ANDing it with the inverse of these bits, which makes sure that Mosey and clock are 0 at this time. Save it in the D register this time. Then writing is a little different. So the first bit that gets written out is kind of weird, and I do that as a special case. And then all the other bits that get written out, I'm going to use this macro. All right. So this is the first bit. We're sending the most significant bit first, and we're going to use the fancy Z80 instruction here to ask, is bit 7 the most significant bit, 1 or 0 in the C register right now? And the C register, remember, is the value that's being written out when you call write 1, write 8 bits out of the C register, okay? Now, where are we? We're down here. So if it's 0, we're fine. The accumulator already has the right value because Mosey and clock are 0. And the key here is make sure that Mosey has the bit value that we're trying to send. So if it's 0, we skip over the OR and we come down here and we just write it out and so on. If it's not 0, that means we want to set Mosey to 1 before we clock the bit over to the SD card. So we're going to OR in that bit. Either way, we're going to send it to the output port. Okay. And remember, the clock will be set to 0. And Mosey will be what's appropriate when this is written out. Then when we're done with that, we're going to set the clock to a 1. It's the only thing that's going to change. And then we're going to output again. Now think about this. When you go look at this clock diagram up here, writing. Okay. So what we did is the first time for the first bit, we made sure the clock was 0. Whether it already was or not, it's 0. And if it is a falling edge or was already 0, it doesn't matter. We can change the value on Mosey at that time. once we've written into it, I mean, an eternity passes before we get to the next instruction. The SD card can run at megabits in speed, and this is only running in a couple of hundred K bits. We don't have to worry about being too fast here, okay? Once we get this thing set out, we then immediately raise up the clock. All right, so every time through this macro here, it's going to do the same thing. A little bit different situation. The first one's priming the thing to get it set up, and the rest are up here. But it's going to do the same thing over and over and over again. And that's where we get this happening here, okay? So each time through, it's going to basically do this much of what's happening. It's going to make the clock low if it's not already low, and it's going to set Mosey to whatever it's supposed to be, high or low. Then it's going to raise the clock, and then it's done. So it's going to do one cycle of the clock. All right. The next time this macro, when we use the macro, it's going to do the same thing. It's going to move the clock down, set the bit on Mosey, then it's going to raise the clock, and it's that rising edge with a stable value on Mosey, which is the indicator to the SD card to take that bit and receive it and process it. Okay. So let's look at how the other 7 bits go out, right? Bits 6 through 0. First one is done like this. The rest are done up here. So why did I feel the need to change the way this works? It's this instruction right there, which is the difference. If you look at this code, yeah, that's the only difference right there, okay? The first time we do this, wow, I wanted to save one instruction. If I literally used the macro, there would be one extra instruction right up here, which arguably may or may not be a big deal. But honestly, when I was doing testing in here and I was tinkering around with this code, I mean, I really was not happy with how long this takes when we're bit banging it like this. And I looked up in the Z80 assembly instructions and stuff, and I determined that, for my understanding, that this is about as fast as I can go without any hardware assist at all. And we can do some better stuff with shift registers and other fancy hardware and change the design if we want. But in terms of the cheapest thing, simplest bit bang interface, this is about as good as I think. This is as good as I could get it. And you can see me, I've listed these are the number of clock ticks per instruction that need to be consumed to do these operations. So, and I was trying to figure out, should I use or some other instruction? Should be shifting? How do I really want to do that? Okay, so what happens here? I got to load A with D, because why do I got to do that? Because the accumulator has to be used to do the I/O operations. It's constantly getting clobbered, and I can't do logic operations on registers that are not the accumulator. So that's why I stored it in D up here, and I can get it back each time I need it. And then I want to say, is the bit in question high or low? This macro is a little different than the read macro. Notice it has a parameter over here. Everything's the same, but this has a parameter called bit pos. So when the macro expands to the write 1 instruction here, when it's invoked and expanded, and the 6 here becomes the value for this label here, this becomes 6, so it says bit pos 6 comma C. That says, is the bit number 6 high or low, right? And it'll set the 0 flag accordingly, and it'll say go down here. If it's 0, just like we saw down here. If it's 1, it falls down here and makes sure that the Mosey is high in the accumulator. And we do the same thing. Do this, which causes the clock to go low, because the D register that kept the copy that we saved over there has the copy of all the right bits, and SSEL is low, and Mosey and clock are 0 in the in the copy that we saved in the D register here. So all at once, when we do this, we're sending then out the new value for Mosey, be it 1 or a 0, and we know, because we've reloaded it from D, that the clock is 0 at that time. Okay, we then OR it to turn it on, and we output it again, and that's the rising edge there. And then we go on and do every other bit. So this is where all the remaining bit cycles come from in this diagram here, okay? So both the read and the write routines only transfer 8 bits. And that's exactly what we want for the SD cards, right? So that's what happens in write 8. Okay, so we're going to call that over and over and over and over again for however many bytes there are in the B register, because that's what DJNZ. Remember, it decrements B by 1. If it's not 0, go back up the loop. Okay, so let's run that one. Let's reload the firmware. Bring my terminal back in here when we're doing that. You can see what happens. Ta-da! So now it says test bits. Here's a little hex dump. The 01, 02, 80, 40 in that order will be written out. So this time I ran it once, and what we got here, this is what the scope says. Now this is still hooked up the same way we saw last time. So we are triggering on the falling edge of the select line here, right? And that's what the blue marker is on this scope here. So what we can see here is, remember I wrote out 4 bytes. I select it. Here's the 4 bytes. I write out 1, 2, 3, 4. Then I deselect it, and the 8 clocks and the 16 clocks associated with the deselection over there, okay? Now, I'm going to reconnect the scope probes like this. So I'm triggering now on the clock. I only have a 2-channel scope. And this probe over here now is on the data line that's coming from the retro board. So this is MOSI, MOSI, master out, all right? So when we look at it now, I'm triggering here. You can see that marker there. And we know, because we just looked at it, and we know this is where the select line goes active. And this gap here is where it goes inactive, right? Because you get the 16 and the 8. So you look closely in here, this is our data. So if we zoom in and move a cursor around on the scope a little bit, we can see this is the first byte. Here's the 8 clocks after the select went active here, right? And this is the MOSI line. And we can see that in this batch of 8 bits, the first rising edge we can see is the first 0 that's transferred from the retro to the SD card, if there was one there, right? So here's the 8 bits. We can clearly see the most significant bit here and the least significant bit here, and that's going to be high there. If we scroll to the right here, I move the cursor over this way, and this is the 01 in binary. We move most significant bit first when we're using the SPI to talk to the SD card. And that's a feature, that's a specification from the SD card spec, not SPI in general. You can do anything you want with SPI, but when you're talking to an SD card, you do the most significant bit first, okay? Here's the second byte. I think I scroll over here and zoom in on that one a little bit. So you can now see this one is all 0 bits, and you see a 1 bit here, and then another 0 bit. Well, that's the 02. You can see the 80 happening here. You can zoom in on that one, which was the next byte, right? 1 high bit followed by 7 zeros, and over here you can start to seeing the 40, right? So clearly this is working. It's writing it out. It's doing it at the right time. For each of these 4 test cases, therefore all other test cases must be perfect, right? And here's another zoom in on what happens. Right here, the cursor's on where we know that the SSEL line must go from 0 to a 1 in here, right? There's the 8 clocks after the data has been transferred with MOSI all high there, and the other 16 that go out after the SSEL has gone back high again. So far, so good. So what's next in line here? All right, let's test reading. Now, in this scenario, this is actually kind of difficult to do, because what we're doing is we're going to just read the data that's coming in on the input bits. That's command 0, test read. Is that what I'm doing here? Yeah, test read. What am I going to do in here? I'm going to print out, what am I doing? I'm going to say A equals 0. Oh, so what I'm going to do is I'm going to print this message, test read, carriage return new line. And then I'm going to say A equals 0x. Then I'm going to call SPI read 8. We just looked at that code. And it's going to return, the accumulator is going to be set to what the bits are that it saw arriving on the MISO pin, which is the data signal that the SD card writes to send data back to the Z80 and the retro board. So, and when we're done with that, I'm going to just call the hex dump A routine, print a carriage return, and then return. Okay? So if we run this, and we don't have an SD card plugged in, and we just leave the board sit there, that pin is floating. Well, remember, MISO right here, that's what we're doing. We're going to shift in bits on here. If they aren't coming from anywhere, then what's going to happen? Remember, MISO over here has this pull-up resistor to 3.3 volts. And that pulls it up enough to look like a 1 on a TTL input, which is what we've got. So what happens is I got no card, nothing's happening, that's just going to be 1, and this is really kind of a crummy test. I wouldn't bet my life on it, but if we read that in, and this is an LS244, it's not an HC, okay? That's why we use an LS for this, to be TTL compatible. It's going to see all 1s. It better print an FF, is my point, if it's just floating. So let's give that a try and see what happens. Let's rerun it again. Bring over the terminal so we watch it go. If I do this, it'll clear the screen. All right, there we go. And let's see what happens. Surprise, surprise. It's an FF. Now, we could rig up a fancy test. But, you know, we're out of time. I've burned up so much time on this video already. Let's just put a jumper on there and connect the MISO pin to ground and run the test again and hope that we just see a 0, 0. Then, you know, maybe it's okay. I mean, again, this is not definitive, but at least it means that it sees the pin. It's doing what we expect it to do. This is not a wonderfully robust test, but it's not bad, okay? It's better than nothing, is what I'm saying here, all right? So let's go ahead and put a little jumper on the board and see what we get. So here's a picture of the board with the jumper on it. I put it from the DO pin over here to ground right there. There's a closer view. So from DO over there to ground right there, all right? So this is going to basically keep the MISO pin low. And voila, we've got a 0, okay? Again, not the best test, but at least lets us know that we're looking at the right pin, and you know, we recognize the fact that there's a voltage on there. So now let's look at the next thing we want to do. This time, what I'm going to do is I'm going to send out 80 clocks, and then I'm going to run what's called command 0. This is actually going to talk to an SD card for real, and the way that the spec says to do so. So what happens is when you really run an SD card and you first turn on the power, what you're supposed to do is send down at least 74 clocks. And since we're sending a multiple of 8 due to the simplistic logic in here, we got to round up to 80. Big deal. So we're going to send down 80 clocks. We're then going to call a routine that I call test command 0. This sends what's called command 0 to the SD card. And the command 0 is what wakes up the card from its kind of inert-ish offline state that it's in when the power first goes on. And if you read the 300-page spec, buried in there, it tells you that if it sees the SSEL line go active and then a command arrive, and it's how it recognizes that I want to put the card into an SPI mode, okay? So this one bit of code here is going to wake up an SD card. It's going to put it in SPI mode. It's going to already have the 80 clocks by the time we get in here, right? And it will Then do the true, right? So it'll send 8 more clocks. It'll set the SSEL to 0, and then it'll send another 8 clocks with the master outline set to 1, which was what we're supposed to do according to the spec. Then I'm going to print a little message that says, hey, I'm going to send this hex value to the card. So it's going to send down a message down here. Okay? It's going to send this. You can see there's a couple of lines in here. What's it going to do? It's going to send this. All right? This is cut and pasted right out of the SD manual that I can't show you. It's on page 265 of the SD Physical Layer Simplified Specification version 8. Simplified. All right? Simplified down to 300 pages. Now, the command for the... we'll talk more about this when we get into the SPI, or rather the SD card details, but it has CRCs, error checking, and stuff like that you're supposed to have in there. But when we're in SPI mode, after command 0 is sent and it acknowledges and it accepts that it's in SPI mode, is my point, by default, the SD card will shut off the CRC checking logic. So we don't have to use it anymore. And the code that I'm going to write is not going to use it in this version. We can always add it later. But with a limited amount of memory, this might actually slow it down and cause so many problems, and which is probably why, by default, they shut it off once you're in SPI mode, is my point. So this exact byte sequence is cut and pasted directly out of the manual, and it says, send this as the message for command 0, and buried in the 95 here is the correct CRC, so we don't have to calculate it. We don't have to write all the code to do that. All right, so already baked in. The command 0 is buried in this byte here. These are the parameters, which are all zeros. They're not really used for this command. And this is the CRC and some trailing bit in there as well. Okay, look at page 265 of the manual, and it explains all that. Okay, all right, so let's go back up here and see how this thing works. I'm going to dump it out so I can see what I'm doing. Then I'm going to send it. And the way I do that is I call SPI write string to write out the 6 bytes and fix my doc, because I'm writing out 6 bytes, not 4. Okay. And then what do? I put F0 into the B register. Okay. And I'm going to use that down here in one of these DJNZ loops. Okay. Now let's see what's going on here. Again, if you poke around in the doc, what happens is when the SD card comes alive and it wakes up, what happens is you send it the command 0. It has a job to do. And when it's done doing that job, it sends a byte back. And that byte that comes back, the documentation refers to as a response, an R1 type response, which means it's a 1-byte response. Now, this is where it gets interesting. The commands in the SD card can take a variable amount of time. So what they tell you to do is to write it down there and continuously clock and read bytes back from the SD card until the value that you get from the card is 01. And keep retrying for a while, okay? We're going to retry up to, looks like 240 times, right? So we're going to do 200 up to 240 reads back from the card. Each time we do this, I want to save my counter because it could get modified in all this code. It most certainly does. And then I want to pop it back down here when I do this decrement and stuff like that, and go around in this loop. Okay, so every time through the loop, it saves the current count value, tries to read a response. If the response is what I want, I say, okay, I'm done. And then I come out down here and I say, yay, all is well. Otherwise, I go round and round and round and round and round and round. And if it never comes back with what I want, eventually the B register will become 0 as a result of all these decrement and try again instructions. If it ever becomes 0, I'm going to print out it didn't work, and I'm going to come back and say, go down here, which is going to turn the SSEL back off again, right? So it's critical that the SSEL goes from, false to true, right? For each command that has to cycle, and that's why we do it up here. I'm going to print some stuff out, so this is going to go really slow. It takes forever for all this to get printed out. Then I'm going to write some data to the card, and I'm going to go in this loop. So let's run this one, and let's run it with the board configured the way it is right now, okay? With meso set to tied low. What's going to happen is it should time out. That's what should happen, okay? So let's go ahead and run this one. See what happens when it fails before we try to do something when it succeeds, right? You got to recognize both cases. I think it's going to spew like mad for all these retries. And it makes sense that it saw all those zeros because we tied it low, right? And it says, oh, it failed after all these retries. So let's go back up to the top. I'm scrolling up here. It might take a minute. There we go. So it says, I'm in the test command 0. Here's the thing I'm going to send. You recognize that. That is the command 0 that I showed you earlier. And every time through the loop, it says it's 0, it's 0, it's 0, it's 0, it's 0. Okay? Perfect. That's what we should see. Let me pull the jumper and run it again, and then it should say all ones. And definitely it did. Okay, perfect. Now let me plug in my SD card, because this will be the first time we actually talk to an SD card, and it should recognize the command 0, and it should respond to it. And lo and behold, it did. So what we did is we wrote this command out to the SD card, and we read a response, and we got all ones, okay? And this is very much a fundamental thing about the SD protocol. What happens is almost everything you ever do will be processed by the card, and while it's processing, it will leave the master in line floating, or it'll drive it high. Okay, and what you need to do is continuously read from the SD card until you see a well-specified bit pattern. And usually what that is you're supposed to read until the most significant bit of one of the bytes is a 0. And that's what it is in this case, all right? It turns out the way I wrote the code, though, is I said run until I get a 0, 1 as the whole byte back, right? And in the command 0, that's one way to do it. It's recognizable and not a bad, it's simple to do. So that's why I did it. So it took 2 tries. Now, if it didn't print this out and waste a ton of time to print this out, it might have taken 50 tries or 100. Okay? So don't think it's just going to happen right away in 2, and why the heck did I do it 240 times? I suspect if we tweak the code, and I'll leave it as a test to the viewer, don't print this out each time in the loop, and then when you're done with the loop, just print out the value that's in the B register if it goes at full speed without all this time wasting while printing. See how many times it goes then, all right? Probably several. So anyway, so what we've just done is we've gotten the card to wake up and reply. So I got to edit this thing. In the next video, we'll talk about the SD card driver at a higher level and all the other commands that are needed in order to get the card to start communicating and reading and writing its blocks of data. All right. So this is an enormous accomplishment. I mean, I swear, when I first wrote this took me forever to debug just to get to this part. You think these videos long? It took days and days of tinkering around just to get the card to wake up and, what's wrong now? What's wrong now? All that frustration. So I kept the good stuff for you guys, right? And the debugged version of the code. Made all kinds of mistakes, but this was, the eyes are now open, okay? So all we need to do now is cobble together a couple more commands and get the bigger buffer transfers to work right to read and write the blocks of the flash, all right? So thanks again. Thanks for watching, and I'll see you next time we do some real data transfers with the SD card.